So here we are, continuing MC4, and you'll see a set of selected questions. So just go through each of these, 1, 2, 3, 4 of them, and answer all of them, and answer them and think about the reasons justifying your answers, and then I'll go through them with you. So question 1, the answer is false. Two objects of different mass collide. The force is equal and opposite. Newton's third law, right? And so if just imagine a collision with a small cart moving, an elastic collision with a spring, a big cart stationary, what's going to happen? This cart's going to bounce back. This cart's going to move very slowly forward. So the velocity and the acceleration isn't equal, but the force is equal. So during the collision, there'll be a force this way on this cart, and there'll be an equal and opposite force this way on this cart. And those forces are always, that interaction is always equal and opposite. So since the force is the same for both in opposite directions, let's just say it's 10 units, that's equal to the mass times the acceleration. So if the mass is 1, the acceleration is 10. If the mass is 10, the acceleration is 1. And so the more massive object undergoes a smaller acceleration, a smaller change in velocity, but the force, the impulse, and the change in momentum are equal and opposite for both objects. They are the same in magnitude, but opposite in direction. Okay, so you see what I'm doing. I'm not just answering the question, I'm thinking through the physics. So every question is a chance to reinforce your understanding of the concepts of momentum, impulse, change in momentum, and conservation of momentum. So a fast-moving and more massive golf club strikes a golf ball. We consider it an isolated system, so there'd be conservation of momentum. And during the collision, the golf ball encounters the same force. We just did that, right? Newton's second law. The time is the same of contact, so the same impulse, and the impulse leads to the same change in momentum. So the loss of momentum of the golf club equals the gain in momentum of the golf ball, but since the golf ball is less massive, it's going to undergo a greater acceleration for all the reasons we just described in the last problem. Question 13, pretty much like the golf ball problem. The bigger cart A has twice the velocity of half of the mass cart B, and half of the velocity, so 1/4 the momentum. But that doesn't really matter, right? When they collide, and they could be moving in the same direction or opposite directions, I just put it that way. But during the collision, for an isolated system, the force has to be the same. The impulse, which is the force times the time, has to be the same because they're in contact at the same time, and that results in the same change in momentum. But the lighter cart B, during the collision, cart B undergoes a greater acceleration because it has less mass and because the momentum has to be the same. Or from the force, mass, acceleration point of view, this is the same. If the mass is less, the acceleration is greater. If the mass is greater, the acceleration has to be less. A different example, but the result is the same. When the gunpowder explodes, there's a force on the cannonball and an equal and opposite force on the cannon. So the force is the same. The impulse is the same because the length of time is the same and the change in momentum is the same, but the lighter mass tennis ball gets the greater acceleration. So it's just another example. Notice how much I like figures. I think thinking in terms of real objects is useful in terms of your understanding. I encourage you to draw figures for all these problems. Okay, here's 3 more questions for section 4. Answer these, pause the video, answer them, and come back. More figures. Momentum in any collision? No, that's false. It has to be isolated from the influence of external forces, and then it's true. So if 2 people on skateboards push off on each other, or one pushes off on the other, then the skateboards are considered frictionless. Momentum will be conserved. But if a person pushes off the wall of a building, the person will go this way. The building does not go that way because it's attached to the ground and the earth. And that's just too massive to think of as an isolated system. So 2 silly putty balls, same mass, same velocity, approach each other. That means they have equal and opposite momentum. If this has 10 units, this has negative 10 units. And so when they meet, they stick together and they fall to the ground. And so the initial momentum was 0, and the final momentum will be 0. And momentum is conserved. It's energy that's not conserved. And we do this in lab with the 2 carts with the Velcro tabs. And you take 2 carts of equal mass and you push them together with equal velocity, and when they stick together, they stop. And again, the initial momentum is equal and opposite. So the total initial momentum of the system is 0, and it ends at 0. The momentum of this goes from 10 to 0, so it loses 10. This goes from negative 10 to 0, so it gains 10. So the change in momentum of each object is not conserved. Only the total momentum of the system is conserved. And the system starts with total momentum and ends with no total momentum. No, it started with 0 and ended with 0. It started with some energy and ended with no energy, because it's what? An inelastic collision. So kinetic energy was lost. And momentum is not conserved. That's not true. Momentum is conserved by the system. Okay, section 5. Here's situation. I'm calling this situation A and situation B, 2 different diagrams. And for each of these, find the total initial momentum, the total final momentum, the change in momentum of object A, and the change in momentum of object B from start to finish. And do that for both situation A and situation B. So that's 8 calculations. So go ahead and do that and then come back. So pretty direct. You just P initial, you add these 2 numbers, you get 45 kilogram meters per second. I didn't write the units. And then the final is just the sum of the 2. It's also 45, so momentum was conserved. The initial and the final is the same. But object A, which collided into object B and slowed down, and object B speeded up. So object A lost some momentum, and object B picked up an equal and opposite amount of momentum. That makes sense because momentum is conserved. And the same thing happened in situation B. This, we start out with a total of 40. We end with a total momentum of 40, so momentum is conserved. But the faster moving object, notice all this is positive, right? All these numbers are positive except for the change in momentum. So the faster one collided, the faster one slowed down, the slower one speeded up, and A dropped by 8 units of momentum, but B increased by 8 units of momentum. And so the total change in momentum of the system is 0, and momentum was conserved. So here we have three situations, A, B, and C, and we're asked to find out in which situations is momentum conserved and in which situations it isn't conserved, and identify all of them. So just do the calculations for all three situations and see what you find and see the results you get. Pause the video and do that, and then come back. Here are the answers I got. Remember, this is negative, so you have to, these are vectors, so negative 32, 18 gives you a negative 14, and in this case, negative 10 and plus 24 gives you a plus 14. So this is not conserved. Here you have a positive 10 and a negative 20, that's negative 10, and a negative 5 and a negative 5 is a negative 10, so yes, momentum is conserved here. And this is a negative 13, plus 5 is a negative 8. But a negative 12 and a positive 6 is a negative 6, so momentum is not conserved in this case. So two more type of problems. Find the momentum of B given these conditions. Pick out the correct vector momentum here. And then a before and after collision. Find out the final velocity of a cart B and pick out the velocity vector out of the selection of vectors. Pause the video, choose your answers, and come back. So we have a 2 and a 1, gives us 3 units of momentum, and we have a 1, so we need a 2 to end up with 3 units of momentum, momentum conservation. And so here's the vector with the 2. I decided to enlarge this so it's easier to see, so if you haven't already answered, you can now answer it and see it more clearly. So notice these are velocity vectors, so we have 3 units of mass, and see the tick mark, 2 units of velocity. So we have 6 units of momentum. This has a mass of 1 and a velocity of 1, so 1 times 1 is 1. So we have total 7 units. We have to end with 7 units. This now has a velocity of 1 and a mass of 3. That's 3, so this has to be 4 in order for it to be equal to 7. And since this is a mass of 1, it must have a velocity of 4. Okay, so think about the physics. Does that make sense? This very massive cart moving pretty fast bumps into a much lighter cart moving slower. What happens? This slows down a little bit because it's so massive, but this speeds up. This slows down just half of its velocity, but this speeds up to 4 times its velocity. Yeah, makes sense physically, right? So here are 2 questions from MOP 6, and take a look, answer them, and then pause the video and come back. The 2 situations are very similar. Here I put people on skateboards. These are kind of skateboards here, and the skaters on ice skates like skateboards. So if 2 people stand stationary, the initial momentum is 0. It doesn't matter whether they push on each other, or 1 pushes on 2, or 2 pushes on 1. It really doesn't matter. The initial momentum of the system is 0, and the final momentum of the system is 0. So the the negative momentum of person 1 has to be equal to the positive momentum of person 2. Those have to be equal and opposite. But if person 2 is twice the mass of person 1, then the velocity of person 1 will be twice as great as the velocity of person 2. Momentum has to be conserved. And the same way in this situation, it doesn't matter whether the masses are equal or not. It doesn't matter which team pushes which other team, whether they push each other. All of the situations, P initial, the total P initial, must be equal to the total P final, and for these kind of situations it's going to be 0 in the beginning and 0 at the end. So in all cases momentum is conserved as long as you have isolated systems. So here's a section 7 problem. Do the calculations and see what you get. Pause the video, do the calculations, and then come back. Okay, there are my answers, calculated answers to the first question, and here are some new numbers, 150 kilograms with new velocities. So redo the calculations for those numbers and see what you get. Okay, there are my answers, and everything works out. Momentum is conserved, keeping in mind that west is negative and east is positive. So in section 7, we were given numbers and we just checked for conservation of momentum. These are section 8 problems. There are actually 1, 2, 3 of them, and here are the instructions. We're assuming the system is isolated and east is positive, west is negative, but we have to calculate these quantities as well as the final velocity. So we're using conservation of momentum, that P initial is equal to P final, and we're getting all of these values plus the final velocity, the final unknown velocity. So start with this problem and do the calculations, pause the video, do the calculations, and come back and see what I have. Okay, so here's the procedure. We have a 140 kilogram cart moving east at 2.25 meters per second. So that gives the red cart a momentum of 315 kilogram meters per second. The blue cart is at rest, so that's 0. So the total starting momentum is 315. By conservation of momentum, the final momentum has to be 315. So if we set the initial equal to the final, that means 315, the initial, is equal to the final. The two masses are stuck together, so m1 plus m2 times the final velocity, because they're stuck together. So there'll only be one final velocity. And so when we take the 315 and divide it by the m1, m2, that's 110 plus 140, or 250. So 315 divided by 250 gives us a final velocity of 1.26 meters per second. And then, so we can get the individual momentum of each one by taking the 126 and multiplying it by the 140, and we get this for the red cart, and then the velocity of 1.26 times 110, and we get this for the momentum of the second cart, and when we add those together we get what we better get, what we should get is that the total final momentum is 315. Okay, try the next one, this one here. So same procedure. I take the 4.6 kilogram cart and multiply it. I change that to 0.52 meters per second, and I get this in kilogram meters per second. The brick is at rest when we drop it, so it's 0, and so the total initial momentum is 0. Once the brick lands on there, the momentum needs to stay the same, but now the mass is the mass of the cart and the brick. So the final momentum divided by the total final mass, which is now 6.4, gives us a velocity of this amount. And I didn't round it out, but I think when you do it in MOPS, you maybe have to round it. Anyway, if I take the unrounded number and multiply it by the 4.6 kilograms, I get this amount of momentum for the cart. And this velocity times the 1.8 kilogram brick, I get this. It should be 0 point. And then when I add them together, it comes out exactly, because I didn't do any rounding, it comes out exactly equal to the what the final momentum should be in order to have conservation of momentum. Okay, there's one more here where the object isn't at rest, and so do that one and come back and check your numbers. Okay, here are my calculations. So 0.75 times 53. I didn't change it this time. I left it in centimeters per second. I get that number. And then 1.250 times 18 centimeters per second. We get this value, and when I add them together I get this, and the final has to be the same. And so if we take the final momentum and divide it by the since it's a single stuck together object, divided by the total mass, we get the velocity of the two objects, and multiplying that number individually by both the masses, the 1.25 and the 0.75, we get these two numbers, and in fact they do add up to what they must add up to is the total final momentum. Okay, here are three problems from section number 9. And let's do the first one and fill in the table, and in this case they don't stick together, so you've got a little bit more calculations to do, but we're assuming the system is isolated, so conservation of momentum will hold true. Okay, here's what I got and how I got it. So the 110 times the 1.2 gives me 132 when it's positive because it's east. And the 155 kilograms times 1.6 is west, so that's a negative 248. So the total momentum, the bigger one is negative, so the total is negative. The final momentum has to be that value. And after the collision, the red cart moves west, negative at 2, so a mass of 110 times 2 is a negative 220 moving west. And so in order for the total to be 116, the blue cart has to have a momentum of 104. So P initial equals P final equals P final red plus P final blue. So P final blue equals the total P final minus, right? Total P final minus P final red. So minus 220 is a plus 220. So plus 220 minus 116 gives you the 104. And since that's the momentum of the final momentum of the blue cart, divided by the mass of the blue cart will give us its velocity. And it comes up to be this number with a lot of digits. And it's in meters per second, and it's positive, it's east. And if you just look at the thing, does it make sense? Okay, so the red cart's moving east, the blue cart has more mass and more velocity moving west, so the total momentum is west, and the blue cart, which is moving west, ends up moving east, and the red cart, which is moving east, bounces back and moves west. So if we can picture that collision, it all seems to make sense. Okay, so there are two more here. The brick problem I'm going to skip because we did one like that. Let's just for practice, I'll do this. You can, if you're doing okay, you don't have. You can just do the assignment. But just in case you want more practice, I'll do this one and give you the numbers before I go on to the last part. So notice this is all to the east, so everything's positive, but the faster moving car collides, it slows down, has less momentum, and the slower moving car gets bumped forward with more momentum, and the total momentum at the end equals the total momentum in the beginning, and that gives you that the velocity of the blue cart went from 0.64 to 1.77, whereas the velocity of the red cart got reduced from 165 to 0.8. So that all makes sense. Okay, here we are finally at the last section, number 10, called proportional reasoning, and here are 4 examples that I pulled out. So look at the first one and let's work through that, and then we'll look at the other 3. So take a look at the first one, see if we can figure it out. So this is a conservation of momentum problem. So you have P initial equals P final, and the initial momentum of the brick is 0. The initial momentum of the cart is 3m times 30 centimeters per second. And that has to be equal to the final momentum, which is going to be the total mass, 3m plus m, so that's 4m, times whatever that final velocity is that we're looking for. And so we divide both sides by m, and we divide both sides by 4. And so we get 3/4 times 30 is 22.5 centimeters per second is our final velocity. Actually, that should be over here. Okay, do the last 3 for practice. Same procedure, P initial equals P final. So m times 6 meters per second plus the stationary skater is 0. At the end, the 2 skaters have a mass of 3m stuck together times the final velocity. Divide both sides by m, divide both sides by 3. And so you get that the final velocity is 2 meters per second. Okay, I think we can stop now, but I'll do the fish. So the big fish, the 5m fish, is sitting there still, and the little fish is moving towards it at 60 centimeters per second. And after they collide, the total mass is going to be 6m. And we want the final velocity. So once again, we divide both sides of the equation by m. We divide both sides by 6. And we get that the final velocity of the big fish and the little fish is 10 centimeters per second in the direction that the little fish was moving. Alright, that's pretty simple once you know what to do. And finally, our table of contents for the last 7 of the MOP, momentum and collision problems with their various times, in case you need it.